Disseminate, a computer science research podcast, the DuckDB in Research series.
Hello and welcome to the DuckDB in Research podcast. In today's episode, we are going to be talking about recursive common table expressions, that is recursive CTEs, and their implementation in DuckDB. And I'm really happy to say that I've got the expert of recursive CTEs with me today, and that is Torsten Grust. Torsten is the Professor of Computer Science at the University of Tübingen. So yeah, welcome to the show, Torsten.
Hi, Jack. I'm really feeling flattered about the invitation to be part of the series. I'm sitting here in my DuckDB t-shirt, ready to talk to DuckDB for the coming hour. So I'm happy to be here. Thank you.
Let's do it. Fantastic. So the first question, or the customary question on the show, is for you to tell the listener a little bit more about yourself and your story and how you got into databases and how you got working with DuckDB. So yeah, let's take it away.
Okay. So I guess I'm one of the older guys that have appeared in your series here. I'm actually a professor in database systems, and I've been a PhD student in database systems since 1994 at University of Constance, Lake Constance, very beautiful scenic area in Germany. And since then, I've been working in databases all the time. So from 1994 until this day, I'm researching databases, in particular query optimization, query processing. I've become a professor in database systems in 2004. And then I've spent time at several other universities, also at TU Munich, where Alfons Kemper and Thomas Neumann are located. Actually, Thomas is my successor. He's sitting in my office, in a sense. Everybody on this podcast will probably know Thomas. He's just a genius. And I joined Tübingen in 2008, having been here ever since, feeling great here, doing database research since then. And well, recently we have switched really lots of our efforts targeting DuckDB, and I'm happy to talk about this here.
Fantastic, cool. So yeah, like I said at the top of the show, we're going to be talking about recursive CTEs today. But I feel it's one of the more advanced topics in SQL is iterative SQL and recursive CTEs. So for the listener who's maybe not familiar with what they are, give us a primer, I guess, of what CTEs are, and then kind of what recursive CTEs are on top of that.
Okay. So CTE, common table expressions, are actually, they come in two flavors. There's the simple, the straightforward flavor, which is the non-recursive CTE, which allows you to assign names to intermediate results that you've computed in your query. And then later on, in subsequent parts of your query, you can refer to that particular name, to that intermediate result, and use that one time, many times, potentially to build on that, and then build up complex queries, compute complex results from these intermediate results. I would say it's a software engineering tool that lets you master and lets you tame complex queries by naming intermediate steps and then referring to them again and again. It's just, I think using CTEs to structure very complex queries is just good practice, good daily practice. And I think these are well accepted everywhere out there. And then there's the sister concept, the recursive common table expression, which really is a different beast. It really adds to the expressivity to what you actually can do with the SQL query language. It's a major step forward. It's a quantum leap for the query language, because with these recursive CTEs, SQL becomes a full-fledged programming language in a sense. It has full expressive power. Just like your general purpose programming language, everything can be done in SQL. Whether everything should be done in SQL, that's probably a different question, because recursive CTEs look awkward to many of us. They tend to be somewhat verbose. They have the bad rep of being inefficient for evaluation. Maybe we can talk about that. But it gives you the ability to iterate inside your query, to iterate until you reach a fixed point or a stable result. And that's something that's really unique to recursive common table expression that you cannot do with regular SQL queries. Has been added to SQL in 1999, has been around for 25 years, and it's still some of the more peculiar exotic features in the query language for sure.
Yeah, so what would be like kind of a common, if I was a user of a database system, when would I be reaching for such for a recursive CTE? What would be sort of the context or an example of when we're like, okay, that's really what I need to be doing here?
Yeah, the textbook example of a recursive query would be to traverse tree-shaped data structure. So if you have tables in your relational database, but if you look at the columns and how they are connected, we are keys and foreign keys. If you're in fact modeling a hierarchical or tree-shaped structure, then a recursive CTE allows you to identify a root or a starting node in that particular tree structure, and then in each iteration of your query, advance from node to node, from the root reach all the child nodes, from these child nodes, reach all the grandchildren. In each iteration, you will explore this hierarchical structure further and collect more nodes, probably matching defined criteria to really explore a tree-shaped or hierarchical data structure of arbitrary depth. If you cannot iterate, then you are confined to explore your data structure to a defined depth. You can join, of course, your table with itself to explore the tree structure, but such a join will be a two-fold join or a three-fold join or four-fold join, which limits the depth you can explore the structure. Recursive common table expressions remove that fixed limit and allow you to traverse as deeply as you need to.
Nice. Kind of on this, and also what you said a second ago about this, the expressive power of SQL, and you can kind of really do anything in it. Is I know that at the university, you solved all of the advent of code. I think it's the 2022 edition, just using pure DuckDB SQL, right? So maybe you can speak to that a second as another example of what things you can do with recursive CTEs.
Yeah, so advent of code is, if probably most listeners have come across that, it's a collection of 25 programming puzzles. Each of these puzzles are posed on the day of December. So it's an advent of programming puzzles. And from day to day, these typically increase in complexity and the challenge increases. But these are programming puzzles that often call you to either traverse tree structures or traverse graph structures or build up graph structures or to perform some optimization task. And this iterative nature of the recursive CTE is just perfect to identify a starting and an end node in a graph structure. And then in each iteration, start from these nodes, explore the graph structure, discard particular nodes that will lead you to cul-de-sacs, explore other nodes, keep iterating over these nodes in the coming iterations, and then explore complex data structures, collect interesting data on your way to solve these programming puzzles. Many of these, I think I'm looking at the 25 days of advent of code from 2022. I bet 80% of these required recursion or iteration to explore these.
Yeah. That's fantastic. Yeah, and I guess that's a really good example for any listener who wants to go and see what kind of recursive CTE looks like in DuckDB. That would be a real good place to go and have a look and have a play around. Cool. So yeah, you also mentioned a second ago about there are certain shortcomings possibly, or like limitations or restrictions of SQL's recursive CTEs. So before we get stuck into kind of DuckDB's recursive CTEs, let's talk a little bit more about the shortcomings of these in general.
Yeah. So when you perform query evaluation in iterative fashion, so parts of your query are evaluated again and again. Of course, you have the problem of infinite iteration. So when will the iteration stop? And to make sure that these, or to at least have some guarantees about when such an iteration will stop, the inventors of SQL, the definition of SQL 99 imposes restrictions on the iterated part of your query. The iterated part has to come to a defined end. The so-called fixed point of the computation. I won't define what that means here. It's a proper abstract algebraic concept here. Yeah. But there's syntactic restrictions that are imposed on CTEs that really make it hard to use CTEs, iterative CTEs or recursive CTEs, as let's say in creative ways. You have cool ideas, you want to express these using your CTEs. Boom, you hit one of these syntactic restrictions, a wall that has been set up probably for good reason, but limits you in what you can actually do in CTEs. And this often leads to rather awkward syntactic workarounds that make these queries look awkward, complex, hard. It probably is one of the reasons why recursive CTEs have a bad reputation in a sense. That's a usability deficiency, I would say. Mm. And that there's efficiency concerns that let the inventors, the definers of SQL 99 of the original recursive CTE standards say, hey, when you iterate, in your iterated query, you can only see the results that you have produced in the immediately preceding iteration. You might be in the 100th iteration, but you can only see the results that you've produced in the 99th iteration. Everything that has been computed before is lost. Well, it's not actually lost. We collect that for you. And later, when the computation is done, we give it back to you. But during the iteration, you cannot see it. It's sort of short-term memory for these iterated CTEs. Yeah. And it's for a good reason. Looking only at the iteration results from the last iteration is probably very few as opposed to the potentially huge log of intermediate results that you have collected in all the prior iterations. So these are where efficiency concerns that lead to these short-term memory semantics of recursive CTEs. You can only see what has been produced in the preceding iteration. And this leads query authors to play dirty tricks like, hey, in my query, I will collect a huge array of stuff that I've produced in the earlier iterations. That is an ever only growing array that will collect and aggregate all the stuff that I've seen during all my whatever tree traversals, graph traversals, and I will pass that on from iteration to iteration as a replacement for this short-term memory in a sense. And that really leads to space leaks, really super huge arrays that you pass from iteration to iteration, slowing down the whole iteration process. And it's really, that's an idiom, it's an anti-pattern, I would say, to carry all this baggage with you, to remember what you've done in the early iterations. It's really unfortunate.
Yeah, you only really want to bring with you the things you actually need, right? But it's okay, cool. But given that then, so I think we set the scene up there perfectly there, Torsten. So let's talk about the DuckDB implementation of recursive CTEs. And obviously you guys at University of Tübingen were behind that. So maybe we can set the scene of kind of like how that came about, how you decided, okay, we're going to be the people to add this into DuckDB, and just set the story there to start off with.
Okay. So I've seen the very first glimpse of DuckDB at SIGMOD 2019 in Amsterdam, when Hannes and Mark were showing the first prototypes of the system, and it looked super interesting, very promising to us. And I was in Amsterdam at that point, and my now postdoc Dennis Hirn, he was with me. We were looking at that system and were really, whoa, this is something new. In-process database management could be really easy to set up, would be ideal teaching tool. Great. And then after the conference, I think on Twitter, I connected with Hannes Mühleisen, the CTO and the CEO of DuckDB Labs. And it said, oh, DuckDB, it's great. It's great. When will you add recursive CTEs? Because the recursive CTEs were missing at that early point. And okay. And then he responded on Twitter saying, oh, probably never. And I was super disappointed. I was super disappointed because in teaching advanced concept of SQL, the recursive CTEs play a role because they really define that quantum leap of expressiveness in the query language. The teaching SQL without having access to iterative CTEs would have been hard for me to imagine. So after that disappointing response on Twitter, here in Tübingen, Dennis set out to write the very first cut at an implementation with recursive. And already back then, we really were delighted to see how clean and how well structured the DuckDB code base was. So adding that to DuckDB was actually a manageable effort. And it has been in DuckDB since version 0.1.5.
Yeah.
That's when we added recursive CTEs in the SQL 99 style, with all these short-term memory deficiencies and all the syntactic restrictions that I was talking about. So, but since then, recursive CTEs are part of DuckDB. So we added a new plan operator that internally has the ability to iterate sub-plan of your query plan. That's actually needed. That's obviously needed to implement the CTE semantics. And since then, we have provided bug fixes and improved the CTE implementation since version 0.1.5. Yes.
Nice. Yeah. Were there any other modifications that needed to be done there other than sort of adding a new plan operator? You said that was the way that the code is structured, it made adding things in really nice, but was there any sort of not like kind of breaking changes that need to be made to support and with recursive?
Well, what you needed is the ability to reset a subplan, to let it run again, in a sense, because upon the next CTE iteration, there's a need to restart a subplan, in a sense. That's something that we had to work on. You have to have this basic functionality when you have a nested loop join in your database system, but we had to work on that particular plan execution feature to reset the plan and evaluate again. Actually, that's until this day, that's a bit of a pain point, because resetting all the plan data structures associated with a sub-plan, restarting a plan anew, in a sense, is a somewhat costly operation that we try to, until this day, try to optimize, make cheaper, and try to work on here in Tübingen. Yeah.
Very nice. That's a nice segue into my next question then. So obviously, given that the first implementation was going by the standard, by the SQL 99 standard, with all the limitations in there, since then, it's been a very fertile ground of research for your group. So, I mean, there's a few places we could start here. I don't know if you have any favorites, but maybe we should start off with maybe the using key and that sort, and how that is built on the existing implementation in DuckDB.
Okay. So the using key feature, actually using key is a modifier that you can add to the with recursive CTE construct in SQL now. And we've very recently added that to DuckDB 1.3. So since 1.3, that's not a research idea or whatever, some whiteboard pipe dream anymore, but it's actually implemented and tested and bug fixed and so on in version 1.3. We have blogged about that. Maybe we can provide a link to the blog post,
of course,
associated with this. Yeah, it would be wonderful. And well, we now see on the Discord that some of DuckDB users have picked that up. I've seen LinkedIn postings of people saying, "Oh, have you seen that using key feature? That's something that's cool, and it's nice to see that this is being picked up." So what does using key mean? So it's an optional modifier that you can attach to your with recursive CTE. And when you do that, the behavior of the CTE, of this iteration process, changes slightly. So in the original CTE, as I said, in the background, the database system is collecting a record, a log of all the intermediate results that all the iterations have been produced. But this log, this record, it's the so-called union table, is over time, it might grow super large. That's why the original CTE definer said, no, we cannot let you access this potentially super large table. This will inhibit efficient implementation or execution of the iterative CTEs. You cannot have that. You have short-term memory. So in using key, we are not just adding, we are not appending or adding to this ever-growing log of information, but we define key columns. And when you see in some iteration a key combination, a key value combination that you have seen before in any of the iterations, then the new information is used to overwrite under this particular key combination the information that you have recorded before. So if in any iteration you have a key value of 100 and you've remembered something under the key value 100, and 200 iterations later, the key 100 comes up again in your computation, then you have the ability to update that particular value saved under the key 100 to store whatever, an augmented and up-to-date version of the information that you want to save under key 100 at this particular point. This means that this record of results that DBMS keeps for you is not an ever-growing heap of stuff, but you have the ability to control, to selectively overwrite and replace old information with new information. That keeps, in general, the recorded information in check. The size of the recorded information is kept in check, and it's kept so much in check, and it's so much smaller in size that we now can allow you in the iterated query to see what you've done in earlier iterations. You can see what you've done. There's no need anymore to collect large arrays of stuff to remember what you have done. The system has the ability to give you, hey, this is what you have seen so far. These are the most recent value that you saved under these key values, key 100, for example. And you can, based on that, you can steer your computation, decide that the iteration is good enough, and then stop the iteration or go on again and so on. So now you have the ability to see what you've done before. And this works because we are not only ever adding to a pile of stuff that is too large, probably by the 1000th iteration. Yeah. That's using key.
Nice. Cool. The question there, so obviously when you were describing that it was very much an overwrite of the key. Is there any way of expressing a more complex semantics of what you want to do? I don't merge the keys or sum the keys when they want. Is that possible as well, or is it very much at the moment just an overwrite? Maybe you don't want to do that. I don't know, but yeah. Sorry.
No. That's very cool. Very cool question. Actually, so because you have access to the current state saved under, say, key 100. Because you have access to that, you can use that currently stored value and add to that, augment that, maintain that particular value, and add on top of that. So that's actually already possible. So it's not just a plain replacement. You can refer to the currently stored value and add to that, aggregate on top of that, decide that the old value is better or is good enough than the current value that you've computed, anything like that. If you find that your query is taking the value that you have already and then perform an addition, to the old value, then we will probably in one of the coming DuckDB versions or variations of using key, we will have a modifier to the using key construct that allows you to say, hey, if there's an old key value, here's a new key value, add it up for me, sum it up for me, so you don't have to manually maintain the particular entries under these key value, under the key 100. The system will automatically do the summing for you. So that's an extension that we are considering. Currently, you would have to use the old value, add the new value on top of that, and then store that as the new value under key 100.
Maybe something for the listener to look forward to in future versions of DuckDB then.
Yeah.
Cool. So, do you have any idea, obviously, with this, adding this feature in, just it sort of broadens the possibilities and maybe makes types of queries possible that weren't possible before. But do you have any sort of idea on benchmarks or numbers of how much speed up of this is or anything like that?
Yeah. So this is about speed up, but this is also about space savings because we are very interested in benchmarking how large will this key store, this key value store, this associated dictionary, whatever you mean, whatever you like as a term for that, how large will that grow? And of course, we want it to be significantly smaller than the pile of stuff that the database would be maintaining in the back with the vanilla with recursive CTEs. So we've implemented a number of classical algorithms, some of these graph algorithms, to see how the using key variant would fare regarding space usage and also regarding time. So we have, for example, implemented a connected components algorithm where each node, depending on its neighborhood and the reachability of other nodes, is assigned to one particular component of the graph. And if you know the compacted components algorithms, in the beginning, every node is located in its own single component. But if you iterate this particular connected components algorithm, then the component that the node belongs to is going to be updated. And that would be a wonderful example for this updating behavior of the using key. The key in this particular approach would be the node ID itself. And the value that you store under that particular key is the component that this particular node belongs to. And every node is only belonging to one particular component. There's no need to pile up a stuff of old irrelevant information. What you need is the most current component that your particular node is belonging to. We have written a paper. We have shown the connected components formulation using key in this particular paper, and it's almost a one-to-one match to the imperatives textbook style connected components algorithm that you can see in your data structures book. It's very nice to see how very elegant and very readable this using key formulation of the DuckDB query becomes. And regarding space savings and time savings, So we have run this on some larger graph with thousands of nodes, tens of thousands of edges, where a vanilla with recursive formulation of the connected components algorithm would have amassed intermediate result information, most of these obsolete, in the gigabyte range, multiple gigabytes of intermediate information, while with recursive, now the using key variant, using key variant uses a whopping 230 kilobytes.
Wow.
Yeah. And in the end, we are by a factor of 270 faster than the vanilla with recursive implementation.
That's a pretty good speed up. Yeah.
That was very nice to see. We have other algorithms like all nodes shortest path. So from each node to each other node, what would be the shortest path to take? And there's some, again, in some of these algorithms, each node saves routing information. So if I'm node X, I want to go to node Y, what would be the next hop, the best hop to go to reach node Y from X? And that's information that is going to be updated. It's iteratively refined. It's going to be updated while the algorithm runs. And again, that would be a perfect example of such a using key use case. And also there, the vanilla with recursive really very quickly runs into out of memory space problems. While we can run, we can run on large graphs, we can run these all node shortest path queries in below 1 second, where vanilla recursive query uses 400 seconds or suffers from OOM.
Fantastic stuff.
There's actually some efficiency, some space and runtime efficiency to be had, and some readability improvements. These queries look nicer, and that's as a researcher and also a teacher who tries to convey these algorithms in SQL style to students, that's also a big win.
Yeah, ticks all the boxes there then. And I think that last point there that you mentioned is historically been undervalued and how important that is, I think, as well, and having that really nice expressive, like you're saying, this is probably one of the impediments as to why these types of SQL queries are not as prevalent as they might be otherwise, is the readability aspect of them as well. Cool. So the other thing that I want to touch on, and it's got a brilliant name, this, and one of your proposals for new CTE variants, and it's trampolines. So can you tell us what trampolines are?
Okay. So actually, in the meantime, I think we have like 3 or 4 different flavors of variants of with recursive or iterative queries on the table. There's one, I will come to trampolines in a second, but
sure, yeah.
Another variant I'm very fond of, and that's the time to live, or the TTL variant, where the query can decide, hey, this is information that I've just computed. I guess it will be relevant for the next 4 iterations. Then it can be discarded. So you set the time to live for that particular information that you've just computed through 4. And then after 4 iterations, that particular row will be forgotten and will never clock your memory again, and so on. There's also some very nice algorithms that have some moving window that they move over some large data structures. You know that the window has a particular certain size. Everything that has left the window will not be relevant anymore. You set the TTL of that particular information, the row that you've computed accordingly. And the TTL variant of this recursive will forget everything in due time. It's also very nice. TTL has not been implemented in DuckDB yet, but this is on the whiteboard here in one of our offices. So it's probably being worked on as we speak here.
Yeah.
And then there's the trampoline version, and I'm very fond of that because it's a collaboration with Thomas Neumann. The Thomas Neumann I was mentioning at Technical University of Munich, who is a great guy and a genius in my eyes, And these trampolines, actually, they are a construct that has its origin and roots in the programming languages world, where you want to efficiently implement recursive functions, and without ever filling up your stack. Okay, so that's actually a recurring theme in the work that we do here in Tübingen. We try to look for and then steal and adapt the best ideas that the programming language and compiler folks have, in particular functional programming folks, and try to massage them and then reuse them in the query languages context. And the trampolines are one particular aspect of that. as I said, originally they were invented to have efficient calling schemes for highly recursive functions. But in the query context, we are using them to define iterative queries where the iterated part has multiple branches of computation that can be active in every iteration. So in one iteration, the first branch might be relevant. In the second iteration, the second branch might be relevant. In the third iteration, the first may be relevant again. And every iteration in every iteration, you can invoke different parts of the logic, perform different parts of computation. That's actually different from normally with recursive CTE, where you have one monolithic query part that is iterated again and again. In a trampoline query, you can identify individual branches, and only some of these, maybe all of them, but normally only some of these are activated in each iteration. So if you when you produce an iteration result, every row is tagged with a branch it is subjected to in the next iteration. So, hey, row, you are meant to be processed by branch 3 in the next iteration. And in the next iteration, that particular row will be routed to branch 3, which will do some cool stuff with that. And other rows might have different fates and may be routed to different branches. And that leads to very cool means to implement all kinds of stuff. It's also the basis for our own research on implementing iterative PL/SQL style UDFs. You can map such imperative programs that have loops and branches and whatever, all these good stuff. You can map these very naturally to these iterated trampoline queries, and branching inside the imperative code would then correspond to selecting the proper branch of your iterated query. And the correspondence is really one-to-one from iterated imperative UDF style code to these trampoline style iterated SQL queries. And we are currently developing compilers for imperative PL SQL style UDFs to these trampoline recursive queries. And that might be maybe this opens the venue to have real PL SQL style UDFs inside database systems that have a facility for CTEs, but never had a PL SQL style interpreter. And DuckDB is among those systems, as you probably know. Yeah. So in secret, nobody is supposed to know this, but in secret, we are working on an implementation for PL SQL style UDFs here in Tübingen for DuckDB based on this trampoline style UDFs, recursive queries. I'm sorry.
Fantastic. Yeah, we're breaking the news here first. The cat's out of the bag now, Torsten. That's it. No, that's fantastic. Cool. So yeah, I want to talk a little bit about impact in the next section of the podcast. Do you have a handle on how much impact your work on recursive CTEs has been in DuckDB in terms of usage and feedback? And yeah, what's that look like for you over the last, I guess, 3 or 4 years, right? I mean, how long ago was Sigmod 2019, right? So like in the last 6 years or so, I guess, or 5 years, yeah.
I think as of today, DuckDB has one of the more efficient implementation of recursive by today. I think it has gone through so many iterations in a sense, implementation wise, that it really is a production ready feature. And if you're out there reading whatever blog posts and other other research on recursive CTEs and iterative computation in SQL, then you can see that DuckDB is one of the platforms now where people try things out. Yeah. Whether DuckDB and recursive CTEs have found their way into production industry use, that I have no data on that, because people tend not to post or blog or bloat about that. But I've seen in the research sphere, you see that DuckDB has become one of the go-to platforms for complex SQL and iterative and recursive SQL by now. And that's very nice to see. Regarding the using key feature, it's super brand new. It's like 3 months in the wild now. And I've seen on the Blue Sky and on LinkedIn several blog posts where people said, "Ooh, this is the game changer. I've written my clunky with recursive CTEs that were inefficient or hard to read. I've rewritten them, and well, yeah, it's a real step forward." But using key, really, that's still in its infancy. So no hard facts about the uptake there in a sense.
Right. Yeah. Just want to pull on it for a second. You mentioned other systems, and we should probably talk about those briefly as well. Like how DuckDB compares to them. Like how much more advanced it is, or more efficient is DuckDB's implementation versus what's out there and what's available in other systems.
Yeah. What's interesting is that there's other relational query language that have been specifically geared to evaluate recursive queries. Datalog, for example. So there's dedicated implementations of Datalog, and Datalog has been built to evaluate recursive queries. And there's implementations out there, very recent implementation of Datalog. One is called Soufflé, and recent research paper suggests that DuckDB can keep up with this dedicated system that has been built to iterate and to evaluate recursive queries efficiently. DuckDB can at least keep up with that and even beat it for a type of query. So we are quite proud of that. And further research in further work on the efficient resetting of subplans and so on will hopefully get some performance advantage for DuckDB, further advantages if all goes well. So I think we are on par with many of the systems out there. Of course, there's the elephant in the room. There's PostgreSQL. I would say that the DuckDB implementation of recursive CTEs has some major advantage over the PostgreSQL variant. In the meantime, we have less syntactic restrictions on there, so very efficient evaluation. I think that using recursive features or queries in DuckDB is just more fun now, because we got rid of many of these syntactic restrictions that hold you back from exploring, being creative with these iterative CTEs.
Yeah, you've liberated us all.
Yeah.
Yeah, free to go wild now. Cool. Yeah. So I guess summarizing then on the future of where you go now with recursive CTEs is there's loads of different angles. So what can we sort of expect over the next year or so, I guess, if you were going to summarize?
Yeah. So regarding using key, we want to, there's some performance improvements that we are currently working on. So if you look at the typical body of such an iterated query, then what you see is that these iterated queries look at what they have computed last and then join that with information or whatever about the tree or graph structure that you would like to traverse. You look at what you've computed last. Oh, that's where my traveler has brought me so far. Then you join that with the graph or tree table to see where you can go next. And because this is such an idiom to join the intermediate results of your CTE with some existing table, we are specifically looking at improving and optimizing these joins. So in using key, we hold the key value, the information about the key values that you have seen and saved so far in a hash table. And that if the hash table can immediately serve as one of the one of the sites of a hash join implementation. So we can save half the work on implementing this join with the tree or graph structure. We can save half the work by just reusing the native using key value data structure and use that as one of the half of this hash join implementation. This should bring another really measurable speed up. We are very keen of measuring that and benchmarking that. It's something that we do. And we will generalize using key, as I said, by giving the system the ability to maintain the values under known keys for you to do whatever max, min, sum, average computation automatically for you. We will, of course, try to add trampolines to DuckDB. Trampolines have already been added to Umbra, which is Thomas Neumann's research style system. And it's fun to play with them there. We want to have trampolines in DuckDB as well. And then maybe, I don't know whether we can add the TTL variant. That's quite a laundry list of stuff.
Yeah.
But, it's a never ending interesting pool of cool ideas. This working with DuckDB is this is something that we try in the next few months, of course.
Yeah.
And then this DuckDB based PL/SQL style UDF thing. This is something we definitely want to try, but this is something for a larger horizon, maybe the next 2 years or something.
Yeah, very nice. A lot of good things, a lot of cool things to look forward to. That's for sure. Nice. Let's change gears. I want to talk a little bit about your teaching with DuckDB. You mentioned it earlier on about how it's become basically the way you teach databases at the University of Tübingen. So, can you tell us a little bit more about that and what that experience is, that what prompted the switch, and how you have found it from kind of before teaching students without DuckDB to now using that, and how that has changed kind of outcomes and student experience and those things as well.
Okay, cool. I'm glad that we find the time to talk about this here. That's great. It's of course close to my heart. Before DuckDB, our database-related teaching efforts were based on Postgres. And that worked well for many years. PostgreSQL is an open source system that's needed for the particular type of course where you want to inspect database internals. How does a buffer manager work? How does query planning work? And so on. And many of the textbook style algorithms out there you find implemented in PostgreSQL. That's nice. But it's equally nice to see that DuckDB is actually incorporating all the cool recent hot research results that you find in papers like adaptive radix trees and vectorized query execution, pipelining, morsel-based parallelism, which are the new cool stuff that you find in research papers. You find all of these almost by the book or by the paper implemented in DuckDB, and that's very motivating for students. If you look at PostgreSQL, you find B+ tree techniques implemented from the 1980s. If you look at DuckDB, you find techniques implemented that have been proposed like in the last, 5 to 8 years or something. Very motivating for students. That's one thing. So we need an open source database system to do particular aspects of teaching. We have to look inside stuff. We have to insert or throw in debug statements, switch stuff on and off to allow students to play with the stuff. And it's installing PostgreSQL can be a real nuisance, can be really hard for, especially on Windows platforms for students who are not very inclined to fiddle at the terminal and so on. Installing DuckDB, as we all know, is pip install DuckDB, and that's it. And that's an advantage that's not to be underrated in the early years of computer science curricula, to have a very pleasant install experience that's consistent across macOS and Linux and Windows and so on. It's not to be underrated. The Python style API, Python would be a language that's known to many of our younger students. This tight integration enables them to do cool stuff, DuckDB, in the second week of the semester or something. It's really refreshing. That's cool. DuckDB SQL dialect is super extensive by now. It's friendly, but it's also very extensive. That means DuckDB is the ideal vehicle for a course that I call Advanced SQL, which is something that you would probably hear after a course on Introduction to Relational Database Systems or something. Advanced SQL really focuses on the dark corners and the interesting corners of SQL, window functions, and of course, it's recursive CTEs and so on. And DuckDB is so rich in implementing very efficiently all kinds of window functions, all the nitty-gritty data, it's recursive CTEs, that this has become the ideal vehicle for advanced SQL teaching here at University of Tübingen. That's a course where you don't learn about select star from group by, but all the other cool stuff that you only find if you flip to page 300 of the SQL textbook. And it's very cool. Students start to implement whatever with these window functions and recursive CTEs, finite state machines, k-means clustering, cellular automata, optimization problems, Sudoku solvers, all kinds of stuff that we do in advent of code style, in a sense, in that lecture.
Have you felt that students have been more satisfied and more interested in databases after the course, given that they're like using DuckDB versus using, say, Postgres? Like, have you found, like, I don't know, maybe by the end of the course last time, like, oh god, I never want to see a database again, but now they're enthused and they're interested in databases and kind of want to pursue it at master's, PhD, or whatever.
Yeah, definitely. There is a saying actually in the database research community that says, would you gift a database system to your best friend as a birthday present or something? And of course, the answer is no, because it's a maintenance nightmare, and installing many of these off-the-shelf database systems out there is a nightmare. Fiddling with DuckDB is just a pleasure, and students have a sense of that this is a system that is moving fast, that development is going rapidly. That's a young system. It's super efficient. Seeing good benchmarks for the DuckDB system really motivates students to take up on that and keep working with that even after these courses. We have a very active influx of students who want to do their whatever bachelor or master thesis with us, and I'm very happy to see that the DuckDB makes these database systems in a sense sexy again. It's really nice. And then there's all this cool gear. You see lots of students carry around their laptops now with DuckDB stickers here on the campus and so on. It's really cool to see.
Yeah, fantastic. We've got a few more sort of high level questions now, Torsten. And the first is your overall. Let me frame it this way. What advice would you give to other sort of would-be developers of DuckDB? People who are thinking of going in there and extending it themselves in some cool way. What would be your advice to them?
I would. The first advice would probably to join the DuckDB Discord, because the community there is so responsive, so friendly, and so positive that I can only recommend to go there and hang out there. I'm there. I'm on there every day. You can find me under the pseudonym of Teggy, which is my nickname, probably most in the SQL channel. Happy to help there. But there's dedicated channels on the internals of the C++ API, the extension, and so on. And people hanging out there are super friendly. So my advice is go there and then start reading a particular piece of C++ code that you are most interested in. Maybe start reading about whatever, adaptive radix trees. Compare that with the particular research paper that you've probably seen out there, and then find the concepts of the paper almost one-to-one in parts. It's like that in the code base, and get a foot inside the code base in that way. So it's a major effort to get to grips, to get to do with the C++ code base in DuckDB. But I think it's really worth it. Don't be turned off by a slew of code that have little documentation and little commentary and so on. It's all structured well. It's named well. It's consistent. Lots of tests there. I think it's manageable. Don't be turned off by the first impression that you might get.
Yeah, that's solid advice. My next one is more of a reflective question on you looking back over your experience of working with DuckDB. What's been the one thing that surprised you and kind of caught you off guard while working with the system?
It's probably the flexibility that's already baked into the engine from the start, and how receptive the engine proved for tweaks and all the additions that we had to do. It's not just regarding the extension system of DuckDB, which is really cool, but really the flexibility baked inside into the kernel itself. It's really cool. So for using key, we had to adapt the so-called aggregate hash table data structure in DuckDB, and it was the API that this structure has was just wonderful to work with, easy to adapt, and so on. So that was very nice to see, and really surprising to us that how forward thinking the engineering of C++, the DuckDB C++ code base is in parts. And then, probably how directly you can find recent research results reflected inside the engine itself. That's also was a very nice surprise.
Yeah, that's very nice for sure. My next question is the penultimate one, and it's more of a recommendation. So it's kind of to the listener, what is your favorite plugin, extension, or feature of DuckDB? You can only choose one. I know there's probably a list of there's loads, but yeah, you can only pick one, Torsten.
Oh, okay. Can I pick one? Well, I would probably...
You can pick one of your own as well.
No, that's fine. I would probably pick the extensive support for array and list processing in DuckDB, using all these built-in functions and the lambdas and the comprehension that have been built into the system. That makes it almost feel like an array or list programming language in a sense. That's something I can only recommend to really get to know well, because on the back end, there's also, it's accompanied by very efficient storage of lists, of large lists, as opposed to systems like PostgreSQL, where large arrays overflow on whatever they're called toast pages or something. And not so in DuckDB, super efficient list storage. And I can only recommend to take the time and dive into the list and array functionality of DuckDB.
There you go, listen. You've got some homework. Go and play with that. Cool. Yeah. The last word now, and that is, what's the one thing you want the listener to take from this chat today?
Yeah. If you have a complex computation problem that needs lots of data, don't give into the knee-jerk reaction. Export the data from the database into some real, making air quotes here, some real programming language, and do all the heavy computation and heavy lifting outside the database kernel. Try to express your complex computation using SQL, maybe using features of the darker corners, or maybe using iterative or recursive SQL CTEs. Compute your results close to the data using scalable query engine as DuckDB provides to you, and don't give in to the urge to whatever, use the database system as a dump data silo only and perform all the cool, interesting stuff outside the database kernel. That's, I would say, unfortunate, to frame it nicely.
Yeah, cool. Let's end it there. It's a good message to end on. Thank you so much for chatting with us today. It's been a really, really insightful chat, and I'm sure the listener will have loved it as well. We'll drop links to everything that we've mentioned in the show notes, so people can go and find all the stuff we've been chatting about. But yeah, thank you very much, Torsten.
Thank you very much, Jack. It's every minute was a pleasure. Thank you.